Bom dia para todos presentes aqui. Bom dia também para quem estiver assistindo no YouTube. Ele já... Bom dia para todo mundo, bom dia para quem estiver acompanhando pelo YouTube. Meu nome é Thiago Gonçalves Souza. A gente está dando continuidade ao primeiro workshop da Cátedra Fulbright, o FPA CISAM. Hoje tenho o prazer de apresentar aqui o professor Benjamin Goldstein. Ele é professor da Universidade de Michigan, da Escola de Meio Ambiente e Sustentabilidade, e hoje vai falar um pouquinho sobre as análises de cadeia de suprimento e do que a gente chama de Life Cycle Assessment. E é isso. Bem-vindo. Thank you so much, Ben. Esse é yours.
Can you hear me? Okay. Bom dia. It's nice to be here in beautiful Belém. Never been to Brazil before. And I've really enjoyed everything I've seen and everything I've eaten. And it's been just a pleasure getting to know the students and the faculty, and the professors, and everyone here. So thank you. Thank you for having me. So as Tiago mentioned, I am Professor Benjamin Goldstein. I am an engineer by training. So I come at and approach sustainability, forests, landscapes, land use change from a different perspective than ecologists. But I think it is complementary, and this will be very different than the first 3 days. But I hope that you'll come away from this seeing that we can really take some of the tools and ideas that I'm going to present and combine that with some of the more traditional ecology and land change science and tools and data from geography and do something much more interesting. So that's my goal, to give you a high-level introduction to getting outside of the forest and the farm and the landscape and thinking about how forests, farms, mines, oil wells, how these changes in the land are connected to systems of production and consumption. And that when we do that, we get a broader picture of what sustainability can be. And this weird circle you see here, it's not just a random AI-generated piece of art. It is the cover of a journal, and the journal is called the Journal of Industrial Ecology. And it's a journal that is the main outlet for the field of industrial ecology. And you might say industrial ecology, that makes no sense, right? Industry can't have an ecology. But the idea is that industry and human systems should be designed around ecosystem principles of balance and of staying within the planet's limits and ensuring that waste that comes out of one industry is food for another industry, much like a food web, right? There's nothing wasted in nature. And that's what industrial ecologists, through engineering analysis, we try to replicate. So the agenda for today is 3 parts, 50 minutes each part, all right? We started a bit late, but that's fine. the first part is really about the foundations of life cycle assessment, all right? So life cycle assessment is a tool that helps you decide and compare products. And we'll get an introduction to the main pieces of that and how we can perform a life cycle assessment in a way that fairly compares different systems. Part 2 will be actually looking at how we build a life cycle assessment, what data go in, some very simple calculations. It's very easy math that we'll be doing today, but a few calculations, just to give you an idea of how life cycle assessment works. We are really only scratching the surface here. It's very, very, very high level. I want you to take away concepts, and if you're interested in life cycle assessment and life cycle thinking, then you can go and start diving into this world. It goes a lot deeper than what I'm showing you today. And then in part 3, we'll look at how we take the information that we get in part 2, right, and turn that into an estimate of environmental impacts from competing systems. So, Victor. Wait, let's see if it loads. No, probably not. Victor, switch it over. I've got a little... I know people love their phones, so this is a chance for you to get out your phone, all right? Or wait, let me see here. I go up here. Wait, I don't need to switch over. I switch over. I'm running off this. You learn something every day. All right. Yeah. Egwa. There we go. Get out your phone. All right. So the first question. Have you heard of life cycle assessment? Oh, that's supposed to say before this course. So before you came here or read about this course and the program for it, had you heard of life cycle assessment? Yes. Okay, we got a yes. Keep going. Give it a minute. Don't worry, there's no wrong answer. I will quiz you at the end, though. Yes. Okay. No. I won't be offended. Let's keep going. Yeah, I see people are still signing in, so we'll let it keep going for a minute. Cool. See, this is more of the balance I was expecting. Life cycle assessment. People think of life cycle and they think, especially ecologists, maybe they think of a butterfly or something. I don't know, right? It comes from a cocoon and a pupa and then turns into the butterfly. Cool. All right. So that was the first. Yeah, okay. So 2-1, right? Most people, the majority, have not heard of life cycle assessment. How many of you have heard of a carbon footprint? Right? Answer this one. Yeah. Give me that. See, this was more of the balance I was expecting right here, yeah? A carbon footprint, people typically know what it is. Yeah. So most people don't know what a life cycle assessment is, but everyone, almost everyone has heard of a carbon footprint. Maybe you don't know what it is. Life cycle assessment is the method to do a carbon footprint. We just don't call it a carbon footprint. It's older than carbon footprinting. It dates back to the 1970s, all right? But in the early 2000s, researchers and oil companies gave it a different name and called it carbon footprint, right? The oil companies, I'm going to get political, actually named it carbon footprint as part of an advertising campaign in order to put the blame of fossil fuel use on the users instead of the oil companies. It was a distraction campaign, all right? So carbon footprint. But life cycle assessment is the foundation of carbon footprint. Cool. And so you're going to come out of here today actually having a feel for how to do a carbon footprint. All right, let's keep going. There we go. So let's get into part one. I'm in the store. I want to buy a chair. I want to buy a sustainable chair. I don't want to ruin the environment. I have a plastic chair and I have a wooden chair. I can't just put them up against a police wall and say, which one of you is better for the environment? Who has the higher carbon footprint? I can't do that, right? There's no obvious answer there. And that's why we need to have tools that allow us to compare products and to quantify their environmental impacts so that we can make informed decisions, right? And that's what the motivation for life cycle is, all right? So it's life cycle assessment. Some people call it life cycle analysis. It's the same thing. And really it is the idea of quantifying the environmental impacts and resource use across all of the stages of production and consumption. We call this the life cycle of a product, right? So here's a diagram. Maybe it's not so clear. It's a little small, but basically it's showing you pulling resources out of the earth, sending them to a factory, turning them into something, using that product, and then eventually throwing it out. Maybe it gets recycled. Maybe it goes to a landfill. And when we do LCA, what we call it, life cycle assessment, LCA, you can estimate the environmental impacts of a product or service. You can compare the performance of different systems. You can tell which one is better relative to another. We can provide a systematic way to holistically capture all of the environmental impacts of products. What it cannot do is determine if something is sustainable. Right? It can tell you if something is more or less environmentally harmful or resource intensive, but it won't tell you, it won't give you the final answer, this is sustainable, that's not sustainable. It cannot determine actual environmental impacts. It estimates, right? It models, and it cannot consider questions of justice and equity, right? We can have very environmentally friendly products, but they're very bad for people. Right? The people who are making them live under terrible conditions, right? So, the product life cycle is at a very abstract level broken down into 5 different stages. We call these life cycle stages, right? And I outlined them before. Starting from the left, we have resource extraction, right? Cutting down trees and mining. Then we have to turn those raw resources into materials. So I know that you do a lot of aluminum production here. So resource extraction is mining. Then you send the bauxite, I don't know, to the refinery where they turn it into aluminum. And then maybe the aluminum goes to a factory where it gets turned into a car door. And it gets incorporated and put into a car. That car gets used, and then it has the end of life, we call it. This is when the car is either thrown out or recycled. You can simplify things. You could just take all of those 3 on the left, those life cycle stages, and just call it production, and then you have 3. Or you can make it more complicated, but the goal is always the same. Looking across the different stages, looking at the energy and materials that go into each stage, looking at the pollution that comes out of each stage, and then summing, adding them all up so that I can get the total environmental impacts, right? Or the total resource use. So from the perspective of our chairs, right, I'm in the store, I'm trying to pick wood or plastic, right? I could have my wood coming from a plantation, or it could be clear cutting from a forest. Then they both go to, the wood goes to a mill, it gets turned into a chair. For my plastic chair, you have to pump oil out of the ground. It gets refined, right, into plastics. It gets manufactured into a chair. And then when we're done using that chair, maybe it goes to a landfill. Maybe it gets incinerated, right, burnt for energy. That's what it means when we look at the product life cycle. So a life cycle assessment is actually, there's a standard formula for doing it. There's a recipe for doing a life cycle assessment, right? And it has 4 different parts. We call them phases, right? 4 phases. So we have the goal and scope. That's what are we studying? What are our main assumptions? What are the systems we're comparing? Then there's the inventory analysis. This is where you actually go out and get data on the materials and energy at those different life cycle stages and the pollution coming out. Then you have the 3rd stage. Let's see here. There we go. Just want to make sure I don't give too much information, which is estimating the impacts. So turning resource use into an impact, like the amount of deforestation or the amount of forest area that you need to actually occupy, or the amount of carbon emissions coming out of your system. And then there's the 4th stage, which is the interpretation, which is that big box on the right, which is always looking at each other phase and trying to see, do my results make sense? Do I need to go back and change my assumptions? Do I need to collect more data? And what can I conclude from my study? So let me just make sure. We're going to focus in on the goal and scope, because I think it's the foundation for the rest of the study. And so this part of the lecture will be, what is a goal and scope? What do we do? And how do we really set up a life cycle assessment so that it is a good comparison between products? So the goal and scope has a few different things that you have to do. You have to explain why you're doing your life cycle assessment. You have to very clearly state what's limited about your life cycle assessment, right? What can't you make decisions on? Because people use life cycle assessment to decide what products to buy. Companies use it to decide what products to produce. Investors use it to decide to invest in a company, right? And so you have to be very clear about what your LCA can and cannot do so you do not mislead people. You have to explain what this LCA is going to be used for, right? Is it going to be used to help design a new product, or is it going to be used to help get investors excited about your company? And number 5 is very important, actually, is for studies that are going to be made public, right, and published, and are going to compare real-life products. You have to actually state that very clearly, because if you do that, then you need to actually have a critical review, which means it's like having a review for an academic article, right? But much tougher and stricter. So you have to make that clear. And then lastly, you have to say who is paying for the study. Because if you are comparing a gasoline car to an electric car, you probably want to know if Shell oil company is paying for this report. Because they probably, that's transparency. Maybe it doesn't influence the results, but you want to know if there are people that have an investment in certain outcomes and decisions, right? So, life cycle assessment has been around since in various forms since the 1970s and 80s. But in 2006, it was actually formalized into an international standard, right? So it has a standard that outlines exactly what you need to do if you want to do a life cycle assessment. What you can do, what you can't do, so that we can actually compare life cycle assessments to each other, and we can be confident in the results that they're giving. Because before this, people were just doing whatever they wanted, right? And so it made it very, very challenging to actually know that a study was well done or not. So now you have to follow this outline, this standard, if you want to do an LCA. At least if you want to publish one professionally. You don't have to follow this standard perfectly if you're publishing in a journal, because that's more experimental, it's science, it's different. So in the goal and scope, according to the standards, the ISO, right, the International Standard Organization, you have to do a few things, all right? You have to explain what your intended application is, right? Am I just looking at comparing two products, or am I developing a label that's going to be on the product to help people make decisions? You have to, again, list your limitations. For example, if I'm only looking at one indicator, carbon emissions, then that means you can't use that study to make decisions about land use or about toxicity, about pollution, right? Or maybe my study is only for the United States. That means I can't take my life cycle assessment to Brazil and make decisions there, right? You have to put this all up front so people know how to use your study. And again, the decision context. Why are you carrying out the study? Let's see here. There we go. Cool. Again, I've gone through all of this. I think the most important part to take away is that critical review. If you read a life cycle assessment published by a company, it will go through a critical review. I've done critical reviews. I've been on the review panel, and you really go in and try and find everything wrong with the study, so that once it finally comes to the public, then it's the best study that it can be, right? And so you have to do that. And if you don't do that, you can get in a lot of trouble. You can be taken to court, right? If I go out and I've worked with Impossible Foods. I don't know if you know Impossible Foods. They make a fake beef, right? It's fake beef that they sell in the United States. I've done studies with them, and they've compared their fake beef to real beef and showing that, okay, greenhouse gas emissions, the carbon footprint of their beef, is 90% lower than real beef. And if you're going to go out and say that publicly, this makes the beef industry look really bad from an environmental standpoint. If you can't show that you did that comparison properly, they're going to take you to court, especially in the United States. So that's why you need to have a critical review. So the goal and scope, let's get into this. The scope is actually where you set the basis, the foundation for your entire study. And the most important pieces that we'll focus on here is really called the functional unit and the reference flow. I'm sorry that life cycle assessment has lots of strange terms and what we call in English jargon. It's like just terms that only people in that profession understand and know. And these are two of those weird terms. A functional unit, what is that? Right? And a reference flow. So, the functional unit is your basis of comparison, all right? LCA, life cycle assessment, provides relative comparisons between systems, right? Beef versus fake beef. Plastic chair versus wooden chair. But how can I compare those two? What's the basis? How do I know that the plastic chair and the wooden chair are providing the same amount of function, right? They're doing the same thing. And that's what the functional unit does, right? It ensures that the systems you're comparing are the same in terms of what they provide, right? So we'll go through a lot of examples of this because this is extremely important. And so there's two ways the functional unit is trying to capture a couple things. The obligatory properties, right? These are the things that your systems have to do, all right? So if we're looking at paint, right, for instance, the obligatory properties of my paint is that it has to actually cover the wall, right? A paint that's very environmentally friendly but is see-through is not very useful, right? So it has to cover the wall. It has to protect that wall against moisture and sun and other stuff. It should be washable. I should be able to clean the paint. And it should be, it should meet health and safety standards. A paint that, and I spelt meat wrong there. I spelt it like hamburger. I don't know why. I must have been hungry when I made the slide. But it has to meet health and safety standards. No, a paint isn't good if you can't walk into, the paint isn't good if you walk into a room and faint because it's so toxic, right? So these are things that your paint has to do. And then there are positioning properties, right? These are things that are nice to have, but you don't need to have them, right? Like, it doesn't drip when you apply it. Maybe it has more colors than the other paint, right? Maybe it's water-based. These are nice things, but you don't need to have it. You can still have a paint that works that doesn't meet those, what we call positioning properties. A classic positioning property is, you know, the little apple symbol on my phone, right? My phone still works without having that, but it's a feature of that phone that makes it different than other phones. So, the functional unit, this basis of comparison, has 5 pieces to it, right? What is the function that's being performed, right? This is often a description of what it's doing. How much function is provided? So how much of that thing is being provided? How long will it provide that function for? Where will you be providing that function? And how well does it perform that function? Okay? So even a simple example, like a light switch, right? The function of a light switch is to turn on and off current, right? How much function is provided? Maybe it's to turn on and off current 10,000 times before it breaks, right? How long will it function for? Maybe that's 10,000 times over 5 years. Where will that be provided? In Brazil, maybe, right? Because that might matter, because there could be safety standards for a light switch in Brazil, that means you have to manufacture it in different ways than a light switch in Germany or United States. And then how well does it perform that function? I don't know if that really matters here, actually. As long as it turns the light on and off, then it's doing its function, right? So not all of these 5 pieces always matter and have to be in there, but you should think through them when you build a functional unit. So here's an example for paint, right? So the functional unit of paint could be the complete coverage of 1 meter squared of a primed outdoor wall for 10 years in Germany in a uniform color at 99.9% opacity. Lots of detail there, right? Very boring, but very important because it tells you exactly what you need to be doing. That means I can't have a product, I can't compare a paint that does all of this to a paint that doesn't do all of this, because those aren't the same systems. They're not doing the same things, okay? And that's why it's critical to get the functional unit correctly. So here's some functional units, right? Some poor functional units. These are bad examples of functional units because they're lacking major pieces to them. So, I want to compare a cotton shirt and a polyester shirt. My functional unit is to provide comfort for the average size person. But this is not good. It doesn't tell you for how long. It doesn't tell you what an average size person is. What is that? Because are they me? Are they someone else? Is this happening in Japan or is it happening in the United States? Because the average size person in those 2 countries can be very different, right? Comparison number 2, another bad functional unit. I want to look at going in a train versus going in a plane. So to transport 500 people, but okay, we know how many people we're transporting, but how far are they going, right? Because that's going to influence how much fuel you need for both of those. Which country are you doing this in? Because a train in Europe is probably electric. A train in the United States is probably diesel, right? How fast are you doing it, right? Maybe you have to transport 500 people on a train 1,000 kilometers in the United States in under 10 hours, right? It's no good to have a train that takes 50 hours to go 1,000 kilometers. You're not really comparing the same systems. They don't have the same function. And then the last one is a packaging material. I get my Amazon package, and it has packaging in it, right? And again, an example of a bad functional unit would be 1 kilogram of packaging. Because the problem there is that we don't use packaging by weight. Packaging is meant to fill out a box, right? It's by volume. This is also a bad, so 1 kilogram of styrofoam provides a very different functional unit than 1 kilogram of like shredded paper. You can fill different volumes of boxes with the same mass. So it is a bad functional unit. So let's say we want to compare 2 light bulbs, right? What is the function of a light bulb? Does anyone? Fernanda. To provide light, right? How do we measure light? What's the unit of light? Are there any agronomists here that work with greenhouses? Hmm? No? Do you have a guess? Yeah, what's the unit of light? What is it? Is it watts? Hertz? That's a frequency. That's how fast, right? Lumens. It's lumens. That's the strength of light, right? So a functional unit for a light bulb should include lumens, right? Because I can have an LED light bulb that uses 4 watts and an incandescent light bulb that uses 100 watts that provide the same number of lumens, right? They'll light up the same area. So maybe something like provide 100 lumens of white light. And you could even put in the frequency if you wanted to. You could say 4,500 hertz or something. You could do that. What are we missing? What's another piece that we need for our functional unit? So we know how much, and we've got these up there. We've got the 5 pieces. How long, right? So, yeah, for how long? For maybe 10 years. What else are we missing? Where? Yeah, where? In Belém, right? And I think that covers it, right? We're providing light. That's the function. This is how much of the function. This is the quality of it, right? It's got to be white light. It's got to be this frequency. And we've got for how long, and we've got where, right? And where is important because the light bulb uses electricity, and different places use different fuels to generate electricity. So my comparison will change if I do it in Belém versus Toronto in Canada, where I'm from, or Ann Arbor, Michigan, where I live. So that is a suitable functional unit. Now I want you to look at these functional units. Talk with your neighbors, okay? If you have neighbors. And take a couple minutes and tell me whether these are good or bad, all right? We've got 3 functional units there. And I think, if I remember correctly, I'll put them back up. Just give me a second. Oh, I broke the computer. Here we go. Come on, you. Cool. We're going to do that. Yes. Okay. You. There we go. So you can actually answer on Mentimeter using your phone. Tell me which ones are good, which ones are bad, right? You can write a little sentence. You could write like, bad are 1 and 2, good is number 3, whatever you want, however you want to write it, okay? But take a few minutes and chat with your neighbors. And then we'll revisit this, okay? Functional unit. We'll give this a few minutes. And I'm not doing anything. I'm just, you guys need to chat with your neighbors, yeah? Victor.
Aqui. Oi, obrigada. Todos entenderam? Conversem entre vocês, próximos, e respondam se aquelas 3 sentenças lá é bom ou ruim. E daqui a pouco ele vai mostrar o QR Code para a gente colocar as respostas. E a resposta é de forma simples. Então, bad, 1 e 2, ou A e B, e good, A, C, ou o contrário, dependendo das respostas. Converse entre vocês.
Good, good, good. Okay. I'm seeing some answers, which I like. So wrap up and if add your response here if you'd like as a group. Hey, Tiago, how's my tempo? Speaking tempo.
You're expecting 50 minutes for this one, right?
Yeah. We started at 9. But I mean, the speed I'm talking at.
Oh, your tempo is good.
Okay, good. I'm trying to go slow. All right. Okay. Okay. So, looking at this, I see some people, yes, okay. So we have bad, bad, good, bad, good, bad, bad, good, bad. I see good, bad, good. And this is the most popular answer right here, actually, is A and B are bad. Yep. And C is good. Let's see here. Bad 1 and 2, good 3. Correct. That is the right answer, right? You can see here. Now, the first one, A, is just comparing materials. It doesn't even tell you what they're doing, right? There's no function there. It's just comparing one material to another in terms of mass. The second one does tell you what it's doing. It's a chair, but still, it's missing many pieces, right? It doesn't have how long. It doesn't have, where it's happening and what quality it's got to do this at. And that's what C actually does, right? It has comparing one dining, that means, a chair that you'll sit and eat at. One indoor chair, providing indoor seating for one adult over a specific period, right? That one provides the information that you need, and there's no ambiguity, right? It's very clear. This is what your chairs have to do. So good, that was good. I see that there was an understanding there. And this is important. The functional unit is important because it influences what we call the reference flow. So the functional unit is what the systems are doing. The reference flow is how much of a product you need to meet the functional unit. Okay? So let's go back to our example of paint. We want to cover 1 meter squared of wall with paint for 10 years in Germany at a uniform color at 99% opacity. We have two paints that we want to compare. Paint A, which is at the top. It is a low water content paint. It requires one application. You only have to put it on once. And you can wait 5 years until you have to put it on again, right? It's just a higher quality paint. You only need 0.15 liters of that paint to meet your functional unit, right? My second paint has high water content. It's thin, right? You need to apply it twice in order to make the wall the same color. And you have to apply it every 2.5 years. So I'm going to need 670 milliliters of that paint to meet the functional unit, right? So the functional unit decides how much resources I actually need to do something, to provide a service, to provide a product. And so getting the functional unit correct is essential, or else you're going to be comparing two systems that aren't the same, and you're not going to estimate the amount of resources that you need, the amount of environmental impacts they will create correctly, because you're not looking at two systems providing the same thing, right? If I don't put 10 years in my functional unit, if I take that out, then you miss the fact that I need to apply more of paint B more frequently in order to keep the wall covered, right? So that's why you need to have all these pieces, at least all of the relevant pieces in your functional unit. Because if it's wrong, then your whole comparison is wrong. And it's not going to help. It might make the wrong decisions. So here is our example of a light bulb, right? We're comparing two light bulbs. Both of these light bulbs provide 100 lumens. We have an LED light bulb that lasts for 10 years. And we have an incandescent light bulb that lasts for 2 years. What are the reference flows required to meet the functional unit of providing 100 lumens of light for 10 years? Let's see here. Yeah, okay, so we got to do this on the board. So, wait, I just erased the thing I want to keep. All right, it's okay. Doesn't matter. So let's write that down quickly. Provide 100 lumens of light for 10 years. I'll just put a Y there. 10 years. My LED light bulb provides 100 lumens of light, and it lasts for 10 years. How many LED light bulbs do I need? This is not a trick question. Huh? 10-year light bulb, 10 years of light. How many bulbs? Anyone? Yes? Huh? No. It lasts for 10 years. So one bulb lasts for 10 years. So how many bulbs do I need? One. Yeah, one light bulb. That's my reference flow for my LED system. LED, one bulb. I don't know what the word is in Portuguese. And then incandescent light bulb. It burns out every 2 years. How many incandescent light bulbs do I need? I see a hand. 5, right? So we have the incandescent bulb. It's got to last for 10 years. Each bulb lasts for 2 years, right? That means 5 bulbs. So that's how many light bulbs I need from each system to provide the functional unit, right? And that's important because you're going to need a lot more energy to manufacture 5 light bulbs than 1 light bulb, right? Is that clear? Yeah? Combinado. Okay, good. So, after we know our functional unit and our reference flows, then we have to say what parts of the life cycle we're actually modeling. You don't always have to model from resource extraction to end of life. You could decide to model different things, all right? So this is where we say what the study scope is. It delineates exactly what life cycle stages you are including in your assessment. You have to clearly state this in your goal and scope, and it should align with the goals of the study. So, example, if the goal of my study is to compare a disposable cup to a reusable cup, then I should include the end of life in my assessment, right? Because that's the whole point of these two systems, is that they have very different ways that you treat them when you're done using them. But that's not always relevant. I'll show you an example. But here, you know, I noticed Belém has some bumpy roads. We also have terrible roads in Michigan, all right? They're no better. And actually, what you see here on the right is an example of a road that they're fixing. And in Michigan, they'll often put a huge piece of metal on top for the cars to drive over temporarily while they're fixing it, okay? And so you could imagine I could have a life cycle that covers, I'm sorry that this is unclear, but the extraction and production of the materials, so extracting iron ore, turning it into pig iron, that's the English term for just iron as a metal. Then you get manufacturing as the next stage, turning that into steel that we then flatten out and roll into these big plates. And then you use it on the road. That's the next stage of the life cycle. And then lastly, it gets disposed of, right? This is the end of life. It might go to a landfill, hopefully not. That's a stupid thing to do with lots of steel. Or maybe it gets recycled, okay? And so this life cycle assessment would cover everything from the start of the life cycle, right, extracting the materials, to the disposal. We call this a cradle to grave life cycle assessment. You're looking at the product from its cradle until it goes and dies, right? Conversely, I could also just look at this. I only include producing the steel and manufacturing it into that flat plate, and then I forget the use and the end of life. This is called a cradle to gate life cycle assessment, because you're only looking to the end of the factory gate, right? When it leaves production and goes to get used, you don't look at that afterwards. So this is called cradle to gate. This one only looks at producing the steel and turning it into a big flat piece of steel for using on the road. And it's going from one factory gate, right, where they take in the raw steel, to another factory gate that is sending the finished product off to the user. So this is called a gate to gate, all right? Gate to gate. So these are just terms. If you ever read a life cycle assessment or a carbon footprint, you might see this, all right? It's a cradle to gate assessment. It's a cradle to grave assessment. So, again, work with a partner. Talk to your neighbors and look through. These are the different processes for producing a wooden chair, okay? I want you to identify which processes are included would be included in a cradle to gate life cycle assessment, all right? Some of them will, and some of them won't. So can you discuss with your friends and decide which ones I would include in a cradle to gate? So remember, a cradle to gate is this one. It includes pulling out the resources, turning them into materials, making a product, but nothing after that. So take a few minutes to do that. Yeah?
Vitor.
Oh,
Oi,
Victor.
gente, então, para a próxima, o que ele está pedindo aqui é leiam as 9 características que ele apontou e indiquem qual que é a tradução que ficou para a gente, cais do fim, onde o que ele quer? Ele quer que a gente pegue o produto, use o produto e depois a gente vai descartar esse produto sem reciclar, sem nada. Então, a gente utiliza para uma coisa e ela não tem... A gente joga depois fora, como se ela não tivesse serventias, como se ela não fosse reciclável. Então, olhem os 9 pontos ali e digam quais delas são usadas dessa forma.
I'll keep that up. I just want to see. Nope. Okay. So, just there's no Mentimeter part for that one. So you can just do this with your friends, neighbors, and see if you can figure it out. And then we'll do it on the board together. But take a couple minutes to do that. Yeah? Cool. One more minute. And then we'll take a break pretty much shortly after. Have some coffee. So, cradle to gate. Let's do it this way. Yes and no. So, do we include transporting the logs? Is that part of it? Is that a yes or a no? If you think yes, put up your hands. All right, I see Fernanda, she's brave, thank you. I see some people over there. Who thinks no? I don't see any. Oh, is that a half hand? Yeah, you think no? But okay, but we need to do that to get to the sawmill, right? So we should include that. So, yes. What about making the chair? Is that part of our cradle to gate? Yes, I see a couple hands back there. Yes, right, correct. Thanks, Dominic. All right. So, 2 is a yes. What about using the chair? Is that a yes or a no? To the left, no. That's a no, thumbs up or thumbs down? All right, that's a no. right? Because that's after the factory gate, right? That's we're ignoring that. What about the sawmill, right? That's where you take the wood in and turn it into actual pieces of timber that you can build stuff out of. Yes? Is that in our is that cradle to gate? Seen some hands? If you think yes, put up your hand. Yeah, all right. I see a majority. You are correct. All right. What about harvesting the tree, cutting it down? Right? Is that a yes or a no? If a yes, put up your hands. I see two. Yeah, that's a no. But it's the cradle. That's the cradle. That's where we're pulling the resources out of the ground. That's the very start of the life cycle. So yes, there's a lot of yeses here. What about landfilling the chair, sending it to the landfill when I break it because I'm angry watching a football match? Yeah? Is that a yes or no? I seeing no? Yeah? No. No. Right there. You guys are good. Right? We do not do that. What about electricity at the furniture store? No, right? That's after the factory. Good. We're not including that. What about the employees driving to the sawmill? This is a tricky one, actually. It's a no. It is a no, right? Because that's not part of the manufacturing process. That is not part of the product itself, okay? We could have a philosophical debate about that later, maybe, but I would say put that in a no. And then what about drying the wood before it goes to the factory? Before the factory. Is that a yes or a no? Yes, right. This is part of the production process, right? So there we go. Thank you for working through that with me. And I just want you to get a feel for what these different scopes include. Last slide, and then we'll break for 10 minutes. When is it okay to actually leave things out? Cradle to grave versus cradle to gate. Well, it's justified when the processes that you are leaving out are the same for both systems. So I was telling you about how I've worked on fake beef versus real beef. Producing them is very different, right? One of them is made from soy and has chemical processing, all types of additives. The real beef, you have to raise a cow, you need feed, you have to slaughter it. But after that, it gets pretty similar. You'll actually use a similar amount of packaging. You will use a similar amount of heat to cook the meat. You will dispose of it in the same way, right? So you can assume that those parts of the life cycle are the same, and you can leave them out because they're not going to be the difference between your systems, okay? So I just want to leave on that note because maybe some people think that cradle to grave, which covers everything, is the only way to do it because it includes everything. But it's actually okay to leave things out. But you have to justify that. So let's come back in 10 minutes and we'll move on to part 2. Okay? Oh yeah, no. Yeah. There you go. Obrigado. Hey Siri, set a timer for 10 minutes.
10 minutes starting.
There we go. Mm-hmm. We're good? Thank you. Thank you. We're going to start again because we got more to do. Cool. Cool. So, first part was about setting the foundation for comparing two products and their environmental performance, right? The key things I want you to take away: functional unit, reference flow. Those are really the main ideas. And then the scope is important to know what's being included. But the functional unit, if you get that wrong, then your life cycle assessment is going to be wrong. Your conclusions will be wrong. So that's the most important. Now we're moving on to what's called life cycle inventory analysis. This is where we actually map out, we make a diagram of the different processes in our system, right? All of those things in the life cycle. And then we get data. We can go and measure the data, or we can get data from databases that have already existing data. And we figure out how much resources are going into each process and how much pollution is coming out of each process. And then we link them together into a system that will then let us calculate environmental impacts, resource use across the entire system. So this is our second phase of the life cycle, right? The first part, goal and scope definition, functional unit, what we're including. Second phase, inventory analysis. This is getting the data to do the assessment. So, how do we do this? And I'm sorry that my slides are not full of pretty maps like some of the other presentations. And I think that should be a takeaway. I'll touch on this again later on at the conclusion, but life cycle assessment often isn't good at capturing differences across space, right? It's not very spatial. But that creates exciting opportunities for different communities to work together. But that's a different piece. So we build a product system, all right? That is the system, that is the collection of processes that produce the reference flow, okay? And so a product system is made up of unit processes, okay? So the unit processes are the individual activities in your life cycle, all right? So if I'm a farmer growing food, right, and I have a farm producing food, right, I'm farming, and I'm making food as an output, let's just say bananas. I would have unit processes that come in. I would have an irrigation process maybe, right? That could be a unit process. I might have fertilizer production as a unit process, all right? I might have a unit process that is using a tractor, right? So that could be tractor operation, right? These could be all different pieces of my system that I need, individual activities that help me produce bananas, all right? And so each unit process has what we call elementary flows. These are flows that either come into my system from nature or leave my system going to nature, okay? So an elementary flow could be something like crude oil that comes into a oil refinery to make natural gas. That could be my elementary flow. And then you need natural gas to make fertilizer, right? And then we could also have elementary flows that leave. So when I burn fuel in my tractor, there's going to be CO2, carbon dioxide. That is an elementary flow leaving my system, okay? And then between these different unit processes, these different activities, there can be waste flows, right? Or there could be product flows. So for instance, a product flow, a movement of mass and energy would be fertilizer. So this could be fertilizer production here. And then the flow coming out would actually be the fertilizer itself, all right? So that's a product coming out of my unit process that's going into my farming system. These can be very complicated. This is zooming in on unit processes, like really highly detailed. So on the left, you can see a unit process that shows you material production or manufacturing. So on the direction of the arrows show you if things are going into that unit process or if they're coming out. So on the very far left, you can see product materials. These might be raw. If this product is steel that is being made in that unit process, then coming in, you'll have crude iron. That could be a product that's coming in. You might also have process materials. This might be things like water and oil that you need to operate the machinery that is making the steel. And you might have waste coming out. And then on the right-hand side of that unit process is the actual steel that's being produced. And then, let me get this up. This will help a bit. Right? And then over on this side, we have a distribution process. So these are processes that move products between other activities, right? And so a distribution process can include things like the packaging for the product, the fuels that you need to transport the product. It can also include waste that might happen during transportation. If I have bananas, right, coming off my farm, and then I distribute them to a store, right, to the market, and I have bananas coming out, and there's distribution here, right? I'm moving them from the farm to the store. I'm probably going to lose some bananas. Some of them are going to spoil. Some of them are going to get crushed, right? So that can also be part of it. So what we do is we just collect all of the important activities that are relevant for our system, and we connect them together into a diagram, all right? So that we get a picture of our system that we're trying to model. And it'll depend on the scope of the assessment, right? You can see cradle to grave on the left-hand side. Over here includes everything. And on the right-hand side, this is cradle to gate. So it's ignoring everything after we've produced the process. I want to make sure I get two terms in here. You can see up here, this says ecosphere. That's basically nature is what that really means. It means ecosystem, more or less, right? Things that are coming out of, to or from nature. The technosphere, again, I'm sorry that we have to use all of these weird terms, but that is the human-controlled system. That's like the economy, more or less. You can think of it that way. And elementary flows cross between the technosphere, so human-dominated systems, and the ecosphere, nature. Just want to make sure I get that in there. So we identify our relevant processes. That is the goal. Here's an example of building a window, okay? And using a window. So the functional unit here is something like use a window that operates for 10 years, that has a certain amount of thermal efficiency in Germany, for instance. And so you can see they've actually built out the product system diagram of all the different functions that go into it, right? And all the different processes. So each one of these boxes is a unit process. So you have window assembly. This is actually making the window. And then the glass that goes into that. To make the glass, you need sand and limestone. You need natural gas, right? To make the window frame, you need other materials. And so you actually identify you build out your diagram and you identify which processes you actually need to include in your system. Some of these are not actually important, all right? So administration, right? The bureaucracy of running your glass factory is not really going to influence your life cycle assessment. And so you wouldn't necessarily collect information on that. So you identify those important processes and you draw out your system, all right? So let's work together and build some diagrams for a plastic chair and a wooden chair. Can this side of the room work with your partners to draw the different processes that go into making a wooden chair, right? So and it's your first time doing this, do not get stressed. It doesn't have to be a work of art. They never are. I'm an engineer, I don't care. Function over form. But draw out a diagram showing the different processes that go into making a wooden chair, right? Like this, something simple. And then this side of the room, do the same thing for a plastic chair. I know there's not as many people here, but work with some partners and draw out a plastic chair so that you get some practice thinking through the life cycle and what a unit process, how we connect individual activities to model a life cycle. So if you could do that, maybe use 5 minutes and do that. We'll reconvene. We'll connect afterwards and we'll see what we found. Can we do that? Maybe give them instructions again. Victor. Yeah. Oh, just repeat what I said. Thank you, Fernanda.
Pessoal, é para vocês construírem esse diagrama de fluxo que ele explicou. Tá? Então, ele trabalha com um parceiro em dupla para vocês desenharem esse processo, isso que ele tinha explicado no quadro. Tá? De uma cadeira de madeira, wooden chair, da floresta até o descarte. Tá bom?
And then
É do lado esquerdo. E do lado direito é para desenhar um diagrama de fluxo de uma cadeira de plástico. Então, vocês vão fazer a cadeira de plástico e...
Plastic,
Ok.
wood.
Do lado de lá é madeira.
Yeah.
Entendeu?
Yeah.
Madeira, plástico,
Uh-huh.
e aí o plástico é do petróleo até o descarte. Beleza?
Yes. And look, you can also look online and get inspiration because there's lots of life cycle assessments. So you can look on Google and try and draw a rough diagram. That's all. On a piece of paper or on your computer. But what are the activities that go into making a chair? And this is different than just the life cycle stages, right? I have explained to you there's extraction, material production, manufacturing, use, end of life. Those are generic life cycle stages. What are the actual processes that go into that life cycle? So use 5 minutes and then we'll reconvene. Maybe one more minute, and then we'll see what people ended up drawing. Cool. All right. Wood. What would be the first activity, unit process in my wood chair? Does anyone want to say? Yeah, forest, right? I'm in the forest. Yeah, of course. The ecologists know this. Yeah, forest. So I'm in the forest and I'm harvesting, right? I'm cutting down my tree, so I'm harvesting. Are there any? What goes into harvesting? What do you need? What would go into that? Yeah, chainsaw? Yeah, right? So I'm gonna need to. I'll probably need some gasoline, probably. I'm gonna need some equipment. Right? And then I'm going to get logs coming out, right? Trees that have been cut down. Then what's after the forest? Any guess? Yeah, transportation, sure. So then I need maybe a truck, right? Transportation, that's going to need probably some diesel, would be my guess. Anything, then where does it go after that? Yeah, the factory, what does the factory make? Is it making the chair? Did I hear mill? No? No. Okay. Because before, you can't just send huge logs to the chair factory, right? They need specific pieces of wood. So first we need to go to, it's called a sawmill, right? And the mill is probably going to take in, it's going to have electricity, right? It's going to have diesel. It's going to probably have like a waste treatment process as well, right? It's going to need water, H2O, and then we'll get to the next one. It goes to the factory, so this is actually manufacturing the chair, right? And so again, you'll need a lot of these similar inputs. You'll probably need diesel. You're probably going to need electricity going in. You're probably going to have another waste treatment process coming out. Probably going to need water. You might need some oil, like for the surface of the chair, right? Lacquer, you call it, or like a finish for the surface. And then we get over to use. I don't know if there's anything that goes into using the chair. Maybe you wash it once in a while, so maybe some soap, right? And so you have soap production. And then this keeps on growing. And then we have the end of life, right? And so maybe it goes to a landfill. And at the landfill, you'll have probably some trucks or bulldozers, some equipment. those are, and probably you need fuel, you have water going in, fuel going in there. And so you can see how your diagram just starts exploding and exploding and exploding, actually, because in order to make fuel, you need a oil refinery, right? In order to make an oil refinery, you need steel, right? And then in order to make steel, you need steel, and you need an oil refinery to make the steel because you need fuel. So you can see how this can turn quickly into a theory of everything, a model of the entire economy. So that's why we need to actually differentiate between what we call foreground and background systems. The foreground system are the systems that, and sorry, plastic chair, I don't think we have time to go through your diagram, but you'll get something similar. And we'll actually go through it this afternoon. But the foreground system are the processes that you control directly and that you can get primary data on. So if I'm doing a life cycle assessment of a farm, my banana farm, my foreground system would be my farm and the inputs going into my farm. I can actually go and measure those, right? And take in an inventory of those. Fertilizer production going into my farm, I don't control that process. That is a global commodity that comes from Morocco or comes from the United Arab Emirates or comes from Brazil. But that's a generic commodity. I don't control that. I can't go get data on that. And these are background processes. These are processes that we just need to get. We can get data from existing databases so that we don't need to go out and collect everything everywhere. We focus on the parts of the system that we control. Maybe if I'm working on a chair and I'm the chair manufacturer, the company that makes the chair, I control my factory, and I might have a direct relationship with a particular sawmill. So these two might be my foreground system. But diesel production, electricity, all of those things are my background system. I don't go and collect, I don't go to the hydroelectric plant and collect data there, right? I just use pre-existing data that exist, right? It makes my life a lot easier. It also makes life cycle assessment expensive because these data are very expensive to get. You can imagine, and I'll show you an example this afternoon, how many inputs and outputs you can have. So the example of the window, you can see right here, I've highlighted the foreground system, right? So that includes manufacturing the window, everything that's happening in the window manufacturing plant, the packaging of it, putting the pieces together. This is all the foreground system because I run the factory. All of the other things are my background system. I don't need primary data on those. So how do we actually build a life cycle inventory? We map out our product system. We figure out what we need to get data on, and then we start collecting the data. So we can have transportation is one type of process that we can use data on. And how do we actually measure transportation is what we call a ton mile or a ton kilometer. So how much work does it take to transport 1 ton of wood 10 kilometers? it's the same amount of work as it takes to transport 10 tons of wood 1 kilometer, right? And so this is how we model transportation in life cycle assessment. It is the distance you're moving something times the mass of that thing that you are moving. And really, a ton kilometer is just another way of measuring work, useful work, right? Work, by definition, is the distance you move something times the force that's moving it. That is the definition according to physics, and that's exactly what a ton kilometer is. It's the mass, which is linearly proportional to force times the distance. So there's lots of existing databases that have the amount of energy, the amount of resources, the life cycle inventory for different types of transportation modes. So you don't have to go out and measure the amount of fuel you need to move 1 ton of wood 10 kilometers. You just go look it up in a table. So this unreadable table over here on the left, you can look at it in your slides, but it tells you how much energy is needed to move 1 ton of freight 1 mile. I know you use metric here. I use metric in Canada. In the US, they don't. 1 mile is 1.625 kilometers. All right? It's a little over 1.5 kilometers. And a ton is 2,000 pounds. So it's about 90% of a metric ton, 900 kilos. But you can see here some interesting things. This is the amount of energy consumed in terms of, it's called British thermal units. It's just energy. It's roughly equal to, I think, 1,055 kilojoules, if I remember correctly. You can see how much energy you need to move 1 ton, 1 mile using a truck, right? It's about 1,500 British thermal units versus a train. It's about 400 British thermal units versus an ocean freighter, right? A big cargo ship. It's 23 BTUs, British thermal units, per ton kilometer. And I think an important takeaway from this is, 1, you don't have to collect these data, they exist. 2, distance and transportation often don't matter that much in the life cycle, right? I can transport something from China 10,000 miles, 10,000 kilometers, very efficiently, actually. It's often, transportation is usually not the most important driver of environmental impacts. And maybe you've heard of food miles, right? And the idea of localizing agriculture so that it's reducing the distance from farm to fork, and that this is a low carbon way to produce food, better for the environment. Generally not true, because transportation only accounts for 10% of the environmental impacts of producing food globally. So localizing agriculture, not that important. If you ask me, there's lots of good reasons to do it, but from a carbon perspective, it's not really important. Here you can see, again, the carbon intensities of different transportation modes, right? This is the grams of carbon per ton kilometer. It's 3 grams of carbon to move 1 ton of goods 1 kilometer on a big cargo ship, compared to 435 if you put it on an airplane, okay? So I think there's a clear hierarchy here of environmental preference when we're looking at different transport modes. Water, better. Roads, worse. Air travel, terrible. And we can do this also for passengers, right? So the passenger kilometer, it's the amount of energy or carbon emissions to move one person 1 kilometer by different transport modes. Again, you can see a domestic flight, 250 grams of carbon per passenger per kilometer. Compare this to a train or an electric car, it's somewhere around 35 grams of carbon, right? So, I just want you to note that these data already exist. You don't need to go collect them. It's already been calculated too many times. And also that there's these hierarchies of transportation sustainability, okay? So what I would like you to do is to estimate the ton kilometers to move 240 kilograms of chairs 150 kilometers. How many ton kilometers is that? You can work alone, you can work with a friend, but I would like you to calculate it, and then I'll go over to the Mentimeter, and you can enter your answer. But 240 kilograms of chairs, 150 kilometers. How many ton kilometers? So, take a couple minutes to do that. Okay? See over here. Cool. And you've got some options. Is it 36 ton kilometers? Is it 36,000 ton kilometers? Is it 6,7?
Sorry. Gente, então ele está pedindo para a gente calcular quantos quilômetros mais ou menos a gente precisa para transportar 240 quilos de cadeira por 150, um trajeto de 150 quilômetros. How many toneladas, toneladas por quilômetros que ele quer.
Someone said 36,000. Keep going. 2 people say 36,000. Two. I'll give you another minute. And you can do this anonymously, right? I'm not going to call you out. It's not like my engineering classes. My mean engineering classes. No one's choosing 6, 7. My son is 8, and he told me 6, 7 is old, like me. He said, now it's 10, 11. Does anyone know where 6, 7 comes from? Anyone? Yeah, Fernanda? Yeah, you do? Yes. That's true. It's from a boy, but where did he get it from? It's from a hip-hop song. It's from a hip-hop song by a Baltimore artist who says 6, 7 in it. No one knows what he meant, though. So there, we got 167. Mission accomplished. Cool. So the correct answer is 36. Right? How many kilograms in a ton? 1,000. So how many tons are we moving? We're moving 0.24 tons. So if you multiply this by that, you're actually doing kilogram kilometers. You have to divide by 1,000. That's where you get the 36. So good learning moment right there, because you have to pay attention to the units, or else everything goes haywire. I don't know. I want to see what the, Confucio. I wanted to see what the translation for haywire would be. Confucio. Okay. There we go. Yeah. No, that's fine. That's a suitable translation. It goes crazy. Yeah? Okay. Let's keep going. And move through this. I'll move a little quicker so we're not here until 10 p.m. Then, so that's transportation. We can also have inventories for producing materials. Let's look at energy. Energy drives climate change, more or less. There's land use change accounts for a chunk of climate change and carbon emissions, but the bulk, most of it, is energy. And so let's just look at energy that goes into producing materials as an example. All right? And so when we build inventories of materials, we have two pieces to it. We have what's called the process energy, or E-process. You can see it up there. That is the energy that goes into actually manipulating the material, changing the material, producing the material. Then we have feedstock energy. This is the energy within the material itself. If I decided to burn that material, there's energy contained within it, right? So an example is a plastic, right? I have an oil refinery that has lots of energy and chemicals and different inputs going into it that will turn raw oil into various plastics, right? And then that is my process energy. My feedstock energy is if I actually just burn the plastic. There's chemical energy in there. It is oil. So that's my feedstock energy. And so the total energy, which we call the energy for material production, is the process energy plus the feedstock energy. This tells me how much energy in total is contained in producing that plastic or any material, right? So here we can see an example of high-density polyethylene, HDPE, used for bottles, used for all types of products. And in the table, which is difficult to read, it actually breaks out the feedstock energy. Let me get this over here. Come on. Yeah. Feedstock energy in megajoules plus the fuel energy. This is the energy in the actual production. And my feedstock energy, if I could zoom this in, would say it says 47.8 megajoules. My fuel energy is 31.5 megajoules. If I add these up, it's roughly 80 megajoules of energy to produce and use 1 kilogram of high-density polyethylene. Same thing for forestry and other types of materials, not just plastics. We have the energy that's within the wood itself. I can burn wood, we all know this. And there's also the energy needed to extract the wood and process the wood. And often we ignore the labor, right? I've just highlighted that again to tell you and remind you that you can't really pay life cycle assessment isn't very good at looking at social components. So, how these workers are being treated is not really a component of a life cycle assessment usually. Lots of databases that you can gather these data from. I just want to throw that up there. You can go look at that book yourself if you want. It's a book by David Pimentel, who actually, I don't know how many years he spent, but he went around collecting data on all the energy that goes into hundreds of agricultural systems, building life cycle assessments. So people have done this for you, so you don't have to do it yourself, because it can get very complicated, right? This is just a rough example of the inputs into a wood production process, which we sort of sketched out here before. And just like with the plastic, we have process energy, which is the fuel to actually transport the wood at the mill, to dry the wood, and we have the feedstock energy. Here you can see two different ways of processing wood. One is called kiln dried. This is when you actually heat the wood and evaporate the water, versus another process called the green process, where you let it dry naturally. And so the total energy for these two can vary a lot. You have your feedstock energy, pretty much the same amount of energy, right? 17.8 megajoules per kilogram of wood. But your process energy is 10 for the kiln dried, closer to 11, and 5 for the green process. And so using these databases, we can start asking questions like, how much non-renewable energy goes into producing kiln-dried wood? And so if my total energy is going to be the sum of my renewable energy plus my non-renewable energy, and so I should define those. Renewable energy is things like hydro, solar, things that we can keep collecting forever without them running out. Hydro, you could argue, is changing because of droughts. And non-renewable energy are energy forms that are limited. We will run out of them eventually. So this is things like fossil fuels. My non-renewable energy is just going to be equal to the amount of total energy minus my renewable energy, right? And so you can start looking at how much non-renewable energy I need per kilogram of wood, or I can look at how much non-renewable energy I need to produce a product. So in this example, a stud is a piece of wood that supports a wall, right? It's behind the wall. You put drywall on it. You hang the drywall. If you have a 3.8 kilogram stud, then the amount of non-renewable energy is 17.5 megajoules. So, right? So if we can start answering different questions now, all right? If a wood stud weighs 3.8 kilograms per stud, what are the total energy impacts per stud? So total energy, let's just call that E total, is going to be 3.8 kilograms per stud times this is my total energy right here, 17.8 megajoules per kilogram of wood. All right. Those cancel out. You do 3.8 times 17.8, you get 3672, somewhere in, if I'm thinking correctly, that should be somewhere in the range of 70, a little bit under that, roughly 70 megajoules. And so you can see that the total energy for a wooden stud is way higher than for a steel stud, actually, right? I can build a steel stud that is going to be it's going to use less energy than my wood stud. Even though people often think wood is sustainable, wood is great, it comes from a forest, we can grow more of it, we actually might need more energy than if we just mine and pull stuff out of the ground. And you can actually also see that the solid waste, if we calculate solid waste, it's going to be much lower though. So the waste for the wood will equal, let's see here, 18.4 grams. So that's 0.184 kilograms of waste per kilogram of wood times 3.8 kilograms of wood per stud. Those cancel out. 0.18 times 4, we're getting somewhere around 72. 0.7, right? 0.72 kilograms of solid waste. So, you can start making these types of comparisons and seeing which materials are actually better or worse across different dimensions. I think this is the last couple of, we got a few slides, but we'll go through these quickly because end of life, we're not going to deal with too much. And it's it's hard to actually model because the data is not very good. But end of life is what you do after you use your product. And there's lots of ways you can treat products. You can incinerate them. You can recycle them and recapture the energy. You can compost them and turn it into soil if it's a biological product. You can landfill them. And because end of life, all of these processes typically don't make a lot of money. They're not very well monitored, to be honest. Like, people really care about what happens inside a factory because if you're not counting how much energy you use and how much steel you use and how much water you use, you're not going to be able to keep track of your expenses, right? So people really keep an eye on all of these types of inputs. A landfill, a recycling center, they often lose money. They're often owned by municipalities. They're often not that well monitored. So the data's tough. There are some interesting processes, though, to keep in mind. Incineration is very popular in Europe. I don't know how popular it is here, but this is when you actually burn your garbage, stuff that you can't recycle, in order to get energy from it, which raises an interesting question because you actually get energy as a byproduct, right, of treating waste. And so now you need to account for this in your life cycle assessment because your product, which is making garbage, is actually producing producing energy. And that means that you might need to produce less energy somewhere else. And so you actually get to take a credit for that, right? You get negative energy use. So it's an interesting process to keep in mind. And there's all types of data that will give you estimates of how much energy you get from burning something, right? So this is where, it's showing you that food and organic waste, you can get 2,000 kilojoules per kilogram of waste that you burn. If you burn plastics, you can get 20,000 kilojoules per kilogram, which is pretty close to actually what I was showing you on the other slides. That's your feedstock energy. Okay. And there's also life cycle inventories that have data for landfilling, for composting, for recycling. I won't go into detail there, but there are some models here that you can look at that provide you information on this. So, I think that's a good time to take another 10-minute break, and we'll come back, and we'll run 5 minutes? Sure. And then we'll come back and do the last maybe half hour, and then we'll be done. Yeah? Yeah, last part is half hour maybe. Sure, we'll take 5 minutes. I can go through the next one pretty quick. Cool. Yeah. Uh-huh.
The practical one.
Mhm.
How long will you take to?
I don't know, maybe an hour and a half.
Okay.
I don't want
No.
it to be that long. Yeah.
Okay, no.
Under 2 hours for sure.
Okay.
Uh-huh.
No, because if you need more time to the part 3, you can also
Oh, yeah.
use
Yeah, sure.
that slot.
Yeah, we'll see. I
The-
think
the-
part 3 is the first part slow, and then the next little. It speeds up pretty quickly.
Great.
Yeah,
No,
yeah.
no, that's because we need to go to have lunch 12,
Uh-huh.
then to come back 1:30
Mhm.
p.m.
Okay. Yeah, sure.
Thank
We need to go.
Oh no, that's I have a meeting.
Uh-huh.
So
Everyone is. Yeah. All right. Okay. We started late,
So
unfortunately.
go rest
Yeah.
5 minutes.
Yeah. Nah.
Take a 5 minutes relax time.
I'll just stay here if we're just gonna start in 5 minutes. I'll go get my coffee and then
You want?
we're gonna go get a coffee. Yeah. 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 Cool. After you.
Thank you.
You're welcome. Hot. Hello. All right, let's get going so we don't run out of time. And this is fairly straightforward, so it shouldn't take as long as some of the other parts. So we've figured out what our systems are, what we want to compare. We've built a model of our system. And then how do we turn that into actual environmental impacts or an estimate of environmental impacts? And that's where the next phase of the life cycle assessment comes in. It's called life cycle impact assessment. So we take our inventory. These could be emissions to the environment or resources that are consumed within our system, and we turn them into estimates of potential environmental impacts. We do this for different types of environmental indicators. In life cycle assessment, we call these impact categories. And these estimates are based on scientific principles. They are fate and effect models. They look at where pollution might go and what types of impacts it might have. So one metric is eutrophication, all right? And so eutrophication is when nutrients run off of land and they go into water. The water becomes nutrient rich. This causes algae to grow. Then the algae dies, and when it degrades, and it consumes oxygen in the water, and then this will damage the ecosystem. The algae itself can also be toxic. So that's what I mean by fate and effect. We look at where the nutrients go, what type of effect they will have, and then we can estimate what the impacts are for eutrophication. So the standard that I mentioned before by the International Standard Organization, they have some rules about how you can and cannot do this phase. I think the most important things to remember, two things. One is that to be a life cycle assessment, you have to compare and include more than one category. So I can't just look at climate change and carbon emissions. That is not a life cycle assessment. That's a carbon footprint. It's a different thing. Even though it's the exact same methods, if you only look at one indicator, it's not a life cycle assessment. Why? Because you might not capture trade-offs between your systems. The second thing is that you are not allowed to combine different indicators into one number. People try to do this. They try to add up climate change to eutrophication, to other things, and they try and give a single score, like this product, my plastic chair has a score of 100, my wooden chair has a score of 85, but you're combining different things and misrepresenting things. So you're not allowed to do that. There are two different types of environmental impacts that we model in life cycle assessment. Emissions-related impacts. These are chemicals that leave the technosphere, right, the economy, and go into nature and cause environmental change. And extraction-related impacts. This is when we extract resources from nature and cause environmental change or limit the amount of future resources that are available. So you can see logging here, mining here as examples of that. So how does this work? You have your inventory. We haven't really looked in detail at inventories, but they can contain hundreds or even thousands of chemicals in them. This is handled by a software that will automatically map each chemical onto the different types of environmental impacts here. So you can see, for instance, nitrous oxides, which are a byproduct of combustion in an engine. They contribute to tropospheric ozone formation, smog, right, which is bad for your lungs. and acid precipitation. Acid rain, which is bad for trees, right? So the software will map your chemicals in your inventory onto the correct categories. And multiple chemicals can map onto a single category, right? So you can see carbon dioxide, methane, CFCs, right? Chemicals and refrigerants, and ozone. They are all greenhouse gases, so they can all contribute to climate change. The software will do this for you, but we'll get an example of doing these calculations. And so there are two different types of indicators in life cycle assessment. One are called midpoint indicators, and the other one is called endpoint indicators. The midpoint indicators, they are earlier in that fate and effect chain. So, for instance, we have greenhouse gases that are emitted. These cause more solar energy to be captured, which increases radiative forcing and the temperature of our planet. So this would be the midpoint, right? We are looking at the change to the state of the environment. How much is the temperature rising? How much are we increasing the amount of energy that's captured by the atmosphere? Then we can look at how that will affect human systems and ecosystems. And that's where the endpoint indicators come in. So the temperature rises, we have more drought, we have melting glaciers, we have extreme weather. This has impacts on human health, on ecosystems, and on resources that are available to us. These are endpoint indicators. And these are often easier to understand, right? Because we know, it's easier to understand and make decisions about how we protect human health than it is based on how many watts of radiative forcing we're actually putting out there. So we call these areas of protection in the life cycle assessment. And the thing to keep in mind is that midpoint indicators have lower uncertainty. They're more scientifically verifiable, right? We know how much, these are things you can measure in a laboratory. I can see how much methane actually heats the atmosphere. I can measure that. These are much more uncertain. It's harder to actually put numbers on those, but people do, and people use them. But I just want you to keep that in mind, because there's a lot of uncertainty when you get over here. How much temperature rise, how much drought it's going to cause, how much food we're going to lose because of that drought, and then how many people might be impacted by that are very speculative. So much more uncertain. And there's lots of these indicators. You can see here, midpoint indicators, there's about 18 of them if you want to. And there's only 3 endpoint indicators. There are competing methods to build these indicators, right? So different laboratories and different research groups have made their own sets of indicators based on what they think the most robust scientific principles are. And so you can pick and choose which set of indicators you want. You just have to state that clearly in your life cycle assessment so people know. So I'm going to go through 3 indicators pretty quickly, and then that sets us up nicely for lunch and the exercise. And we're going to stick with midpoint indicators. We're not doing endpoints. I don't play around with endpoints. I think they're too uncertain, but they are there, and you might run into them if you read a life cycle assessment. So global warming, some people call it global warming potential. Right here you can see this is one set of midpoint indicators. Here's another research group, they called it climate change. It's the same thing in both of them. So climate change, I think we all know, is happening because we are absorbing some of the radiation that bounces off the planet, and it is the low wave radiation that is being captured in the atmosphere by these greenhouse gases that we are emitting more and more of. If you look at that diagram and zoomed in, you'll see that the human amount, the actual scale of extra greenhouse gases added to the atmosphere by humans is pretty small relative to a lot of like global biogeochemical processes, but it's adding a little bit more each year. And you can see each year, this is our global average temperature since 1880, and you can see how even though we're just adding a little bit at a time, we're knocking things off balance, right? And so you can see the more it gets outside, the hotter it is, right? So we are changing our climate, obviously, right? And I think that's a pretty cool diagram showing you how things have really moved off of stability since last century. So there's 2 midpoint indicators for climate change. We're going to focus on one. You can do global warming potential. So this is a quantification of how much energy is being captured by the greenhouse gas, or you can do global temperature potential, which is how much that greenhouse gas will actually raise the temperature. We will stick with this one, okay? Global warming potential. So what is it? Global warming potential really is, it is how much a gas will heat the earth relative to CO2, because we have tons of different greenhouse gases, lots of different types of greenhouse gases. We have methane, we have nitrous oxide, we have CFCs, and they're not all equal. So how do we turn these into a single unit that we can actually compare? Right? If I'm making beef, my cow it's having enteric fermentation, it is farting and releasing methane, right, and burping. And also we have CO2 that's part of the production of the feed, right, when we cut down forests and it releases CO2 through the atmosphere. How do we add these up, right? They're 2 different greenhouse gases. Well, we use the relative global warming potential. We say how much of this gas, or how much CO2 would you have to emit to have the similar amount of global warming as the gas that you're releasing, right? And so basically you look at the 2 different lifetimes of those gases in the atmosphere and how much energy they would capture, and you take the ratio of the 2. And so you don't have to do this. It's already all out there. The International Panel on Climate Change, Intergovernmental Panel on Climate Change has already calculated all of these. So how much CO2, if I emit 1 kilogram of CO2 to the atmosphere, that is equal to 1 kilogram of CO2 global warming potential. If I emit 1 kilogram of methane, that's equal to 27 kilograms of CO2, because it warms up the earth 27 more times than CO2 does. It captures more energy. Nitrous oxide is 273 times more potent than CO2. So you take every gas that you're emitting in your inventory and you multiply it by this conversion factor to get the equivalent amount of CO2, right? So here's an example of Brazilian beef, right? Hey, yeah, Brazilian beef, good. And so if I wanted to know what's the global warming potential of this, it emits 6.4 kilograms of CO2. And you're going to multiply by the global warming potential, which is that little chart there. It's 1 kilogram of CO2 equivalent per kilogram of CO2. And then I'm going to add that to the methane. I have 0.42 kilograms of methane that are released when I produce my cow. I'm going to multiply that by 27.9. Because if I release 1 kilogram of methane, it's equal to 27.9 kilograms of CO2. And then the last thing, you do the same thing with nitrous oxide. You have 0.02 kilograms, and you would use the conversion factor 273. And then you just add these up. and it will tell you the equivalent amount of CO2 that is being released to the atmosphere by releasing all of these different greenhouse gases. It finds a way to take different chemicals and put them into a common unit. All right? So that's why when you see a carbon footprint, it will say something like 1 kilogram of beef is equal to 25 kilograms of CO2 equivalents, because it's equivalent to that much CO2. And you'll often see it written like this, CO2E. All right? So that's what that means if you see that. I was going to have you do an exercise. We will jump over that simply because of the time. But basically the exact same thing. I wanted you to figure out what's the global warming impacts of the US economy in 2022. We have how much CO2, we have the amount of methane, and we have the amount of nitrous oxide. Same calculation as right here. You multiply the chemical times its emissions factor, right? This table here, it's global warming potential. And then you sum them up to get the total amount of CO2. And we'll do this in our exercise later. There's no rush to do that now. And actually there is, just like there's a guide and a rule book for life cycle assessment, there's also a rule book for carbon footprinting. It's called PAS 2050. Same idea. It tells you the rules for doing carbon footprinting. But really, carbon footprinting is a subset of life cycle assessment. And we've done at the University of Michigan tons of carbon footprints. Jim and I have worked on some cool stuff, mapping the carbon footprints of beef, chicken, and pork consumption across the United States. You can go look that up. We've published that last year in Nature Climate Change. And I just want to end on one, at least for carbon, I want to end on this. It gets tricky when we start talking about forest products. And this is why we need ecologists in the conversation, because engineers like me often assumed that wood products are carbon neutral, right? Because the wood, photosynthesis, collects the CO2 from the atmosphere. If I cut down the tree and then burn it for energy, it's the same amount of CO2 that goes up. Right? That's what we assumed, at least. And then we said, well, the forest is going to grow that CO2 back anyway, or the tree back anyways, maybe. So then it sucks it back in, so it's carbon neutral. But that's wrong for a couple reasons. One is that forests don't react like that. When we cut them down, there can be emissions from the soil. They might not grow back properly. We ruin the ecosystem. Second reason is that the timing matters, right? So I have time here, I have CO2 emissions here, and let's just say that this is 0, so above this is a positive emission to the atmosphere, below here is negative, right? I might cut down my tree at year 0 and burn it here, and yes, maybe the forest will grow back, but it grows back slowly over time, right? It's not sucking all that carbon in immediately. So this carbon is causing global warming already. This carbon is slowly getting sucked out. So even if it is carbon neutral, it's not climate neutral. Those are different things. Does that make sense? So some people have tried to account for this using biogenic carbon factors for global warming potential. I just want you to be aware of them. And I want you to know that they are wrong, and that this is why I think this is a very exciting way for our communities, ecology, to connect to the engineers to help us model these processes better. And that's exactly what LASER is actually all about. The last two things I'll talk about very briefly is 2 other impact categories that we will do in the exercise. So I'll just go over them quickly, and then we'll get to play around with it in the exercise anyways. Acid rain. This happens when we release sulfur dioxide, nitrous oxide, when we burn fossil fuels. It goes into the atmosphere, it goes into clouds, it turns into an acid, gets rained down and causes damage to ecosystems, all right? So you can see here, this is what a forest looks like when acid rain hits it. And this was a big problem in Canada and the US, which is why you see the Prime Minister of Canada and the President of the US signing an agreement in the late 1980s to stop acid rain. And it's the exact same mechanics as global warming potential. You get the amount of chemicals that are being released in your inventory, right? You have your inventory that you've built that tells you all of the different acids that are being released to the atmosphere, and then you convert them into a common unit, right? In this case, it is sulfur dioxide equivalents. So if I release different chemicals to the atmosphere, what is the equivalent amount of sulfur dioxide that I'm releasing, and how much damage does that cause? So exact same thing. You're multiplying one number by another. Last one is eutrophication. I talked about this before, right? We have nutrients that enter water streams. They cause algae to grow. The algae dies. It sucks up the oxygen and kills the fish, right? And this is a huge problem. This is what it looks like, right? You can see here, this is the Gulf of Mexico, or as the US likes to say, the Gulf of America. And you can see that it is receiving all of the nutrient runoff from the Mississippi River. So that's what it's showing you up on the right over here. And it turns into a huge cloud of pollution that is actually, let's see here, it is 17,000 kilometers squared of a zone in the Gulf of Mexico that is too low in oxygen for fish to survive for large portions of the year, right? Exact same mechanism when we want to calculate it. We look at our inventory, which chemicals are coming out of our system to the environment, and then we get the factor that we multiply it by to turn it into a common unit. In this case, it's kilograms of phosphorus. So what's the equivalent amount of phosphorus I would need to dump into the water in order to cause the same amount of eutrophication? So you can see here phosphate, which is a popular fertilizer, is about 1/3 as potent as 1 kilogram of pure phosphorus. We're going to practice these calculations in the exercise, but in reality, the software that you use to do a life cycle assessment will do this for you. And same thing for aquatic eutrophication, right? So this is freshwater eutrophication. Often the nutrient that limits algae growth in freshwater is phosphorus. In marine environments, it's actually nitrogen, and that's why for marine eutrophication, it is the amount of nitrogen that you would need to throw into the seawater. That's your common unit. So, mechanism is the same as I showed you before. Emissions times what we call this characterization factor, that's the term for it, gives you your potential impacts. And that's what we'll be playing with in the afternoon. And so I'll conclude just by talking about interpretation. And we won't do this in our exercise. I just want you to know that it exists. And this is the part of your life cycle assessment where you actually check to see that your results make sense. If they don't make sense, do I need new data? Do I need to change my model? Do I need to do something else? Do I need to change my assumptions? And once you're comfortable with what your model's telling you, that's when you actually start drawing conclusions. So I will end on that. We're 1 minute early, and we'll get to explore this more hands-on in the afternoon. So thank you for being patient, and sorry for the late start, but we made it work.
Thank you, Ben. It was very interesting and worrying. Thank you for. Obrigado, gente, quem está assistindo a gente pelo YouTube. Nossa transmissão termina aqui. E amanhã tem transmissão ao vivo. Então, a gente finaliza a transmissão com vocês. E, se vocês tiverem dúvidas ou questões, podem entrar em contato com a Cátedra Fulbright, o FPA CISAM, que a gente pode passar os e-mails dos professores, se vocês tiverem algum interesse de contato. Obrigada.
Hello, hello.
Gente, 1h30, a gente retorna agora para as atividades da tarde, para fazer os exercícios que ele vai